Yeah, we have another one from Lars Dietman. I think it's a little bit comparable, let's say that way, but it shows that we have to do things on pure optical switching. But I think it's quite interesting to see all these options already now, so that we can think about it. Lars is from the Technical University of Denmark. Oh no, sorry. He's there, still there. He studied there, but he is still working there in the research center. And since 1999, he's heading the network competence area on optical and physical networks. The floor is yours,
Okay,
Lars.
thank you. Yes, my name is Lars Dittmann, and I will also be talking about optical packet switching. I've kind of divided my talk into two parts. First, something general about optical networking and optical packet switching, and then I will present some results from an IST program called David from the 5th framework program that's about to complete, and I'll show some of the way that we have decided to implement an optical packet switch network to evaluate the possibilities and also the technological challenges in implementing such a network, because it's not an easy thing. And this is also one of the things I'll discuss in the introduction about what are the feasibility of using optical technologies at packet level. First of all, we must be aware that the optics have played an important role in lowering the price of transmission. I know a lot of people are surprised about how the cost and the speed of the computer has gone up. Today you can get several gigahertz computers very cheap, but actually the cost of optical transmission have decreased much faster than the development of CPU speeds. And if we can do the same for the network nodes as with what we have done for the transmission in optics, of course that could be of very beneficial to lower the cost of the network nodes. So of course it would be very nice if we could implement all optical networks in which the information stays in the optical domain from the place where it leaves the terminal or user until it reaches the final destination. It might not be possible, but then we can do some intermediate links where we are implementing an all optical network. All optical network or optical network have been a terminology that's been used for many years, but actually it's never been used. It's never been real optical networks. We have had the SDH SONET network, SONET's synchronous optical network, but it's not an optical network. It's optical transmission used in a network. So if we look at the future of optical photonic networks, we should see it as different stages. Of course, there will be some extensions to SDH SONET networks where you have a more dynamic configuration of the containers in the SDH. There are activities like ASIN, GMPLS, also presented by Didier. There are some ways of doing virtual concatenation with the LCAS, generic framing protocol for encapsulating Ethernet frames in a better way, and all that stuff. And that, for some people, that's still optical networking. To me, that's not optical networking. That is electrical networking using optical transmission. So the next stage, of course, will be that we'll have transparent optical networks where we have electronics for the control and the management of these networks, but the data path will be all optical. And there's a lot of advantages of that. One of it for doing it is that the conversion from optics to electronics is very expensive. So if we can remove that expense from the network, we can definitely provide much higher capacity at almost no price. And of course, the final stage will be that we can replace everything by optics, and I'll make a comment on that at the final slide. So why do we need the next generation optical networks? One thing is, or perhaps the most important thing, is cost reduction. Network capacity is still very expensive. These huge carrier class IP routers are still very expensive, and we need to find ways to restructure our networks to lower this price. I know that in research networks, it's become a commonality to have several 100 megabits of capacity or gigabits capacity in the backbone trunks. But when we talk about providing broadband connectivity to all users, we need huge capacity. Means network nodes with several terabytes of capacity in transmission capacity. So we need that to do that. Unfortunately, when we start to work on optical networks, we need to redesign the network. We cannot just replace what we currently have with optical counterparts. We need to find other ways of doing it. And finally, also, we see the optical networks, the next generation optical networks, in line with what's generally happening in the network today, that some of the more complex functionalities, because of the required speed, is moving to the edges. And what we see today is also that the concept we have tried to look at in the David project is in line with the MPLS concept of having some more intelligent functionality on the edges, and then a very simple core path. Possibly a layer 2 core path. When we talk about how to structure the networks, there are different possibilities. I've just on the slide listed that we should not forget about circuit switching. Of course, packet switching is a very attractive thing. It provides a lot of flexibility. But if there's no variation in the traffic, then why do packet switching? We might do packet switching towards the applications, towards the services, but in the lower part, in the physical infrastructure, we should be aware not just to do it because it's fancy, because it's nice to have, we should also think about the cost. There are different ways of doing packet switching as well. Not been mentioned that much, but the difference between the burst and the packet switching is mainly a time factor, where we have a very huge amount of data that we can send. And burst switching is also what you can call very fast circuit switching. So there's a linkage between burst and circuit switching in that respect. The selection of circuit switching, burst switching, and packet switching has very much to do about the size of the information that we like to send and how fast we can reconfigure our networks. So definitely the packet switching is about transmitting small units in a very short time. Okay, thank you. So packet switching about transmitting very small units. And of course, for some applications, that's very nice to have if we talk about traffic originating from a single flow. But if we talk about aggregated traffic, we should also be aware that there are other technologies. But today I'll mainly talk about how we can do the packet switching, and then it will be up to you to decide whether it's feasible to do packet switching in the optical domain as well. Primarily because optical networking would probably be a layer 2 at the most. It will probably never be a layer 3 functionality. Then why do packet switching at all? Packet switching in the optical domain is primarily a traffic engineering tool. It's very nice to have because it provides the flexibility. But we must always be aware that we should justify this flexibility. Flexibility costs. And it's always more expensive to do packet switching than to do circuit switching. Maybe some people believe that an IP router is much cheaper than a telephone exchange. Actually, a telephone exchange is much cheaper than an IP router if you talk about the amount of capacity it handles. Maybe the price structure from the manufacturers is not reflecting that, but definitely it's much cheaper to implement a telephone exchange. So we must justify the use of packet switching. Also, the argument that we should have a packet switch transport network because the applications are packet oriented is, to me, a complete mistake. Of course, we should have packet-based operation at the application level because we know that application today requires a flexible amount of bandwidth. But when you look at aggregated traffic in the network, of course, there are some assumptions about how the traffic looks, whether we do have self-similar things in aggregated traffic as well. Then we might need traffic switching packet switching in the transport network. But if we don't have this, we should be aware not to mix it up. So packet-based operation at the application level, because all future applications will be IP-based, doesn't mean that we need to do packet switching in the optical transport layer as well. That, to me, is an important thing to mention. And another reason why you should do packet switching is that we might be able to provide some better resilient mechanism in the network. Today, you can either do it in SDH network, and you can then lose at least half of the whole capacity of the network, or you could do it at the IP level, but then the response time is much longer than what you normally see in the transport layer. But by doing this, we can do a more flexible resiliency concept in the transport network. If we look at the step towards optical packet and burst switching, then I mentioned in the first slide that there are different scenarios to go for. And the second stage, in which the data path becomes all optical, is illustrated in this slide, both showing what we do if it's about packet or label switching, where we evaluate the label of the packet electronically. We create a new label, and then we add the new label in the optical domain on the output. But the content of the packet will pass through the network transparently in the optical domain. We could also make burst switching, in which we are sampling the bursts and chopping up the burst and sending them out again on the other side. So again, the user data will be transparent, pass through the optical network, whereas all the information used by the network to find out the destination, for monitoring the quality of the network, is all done in electronics. And this is one of the approaches that we have followed in the DAVID project. DAVID stands for Data and Voice Integrated over Dense WDM. It might be a little strange title for an optical packet switch project, but the intention was to demonstrate that we, within the optical domain, could implement a packet-oriented transmission concept in which we can make priorities in such that we could handle both delay-sensitive application like voice and loss-sensitive application like data. So we can do a scheduling in the optical domain, and we can prioritize optical packets in such a way that we could go for this. And we actually just this January had the first transmission of real-time applications in our demonstrator, where we demonstrated voice and video transmission originating from a legacy network passing through the optical packet network. As I mentioned, this is a project funded by the European Commission under the 5th Framework Program, the IST sub-program of that. And the timeline of it was that it started in July 2000, and it will end in October 2003. In relation with the conference in Paris, there will be the possibility to go and publicly see the demonstrated testbed just outside of Paris. So the goal was to develop a concept for making a network based on optical packet switching being the ultimate flexibility, and also to develop and look into how we are controlling, how we are managing such a network. Just a list of the partners, some companies, Alcatel as the main suppliers of the equipment technology, network operators looking into, fortunately all classical network operators, looking into the requirements of such a technology before they would like to introduce that into the network. Some research centers and universities involved. There's a lot of universities involved in the project, also seeing that this is fairly long-term research. The overall architecture, you see in this slide in about an hour ago when Didier presented his overview of the project, is showing the architecture of the network. In the network, we're both considering the two different parts of a classical telecommunication network. The metropolitan area network, where we are aggregating traffic from a number of legacy networks, and the wide area network that is used to interconnect these metropolitan area networks. What we are aiming for is having an all-optical transmission within the metropolitan area network and an all-optical transmission within the wide area network. But when we are moving from one network, and you can also see the topology is different in the different areas of the network, and actually also the packet format that we're using is different in the different areas, because we are within the wide area network, we are aggregating traffic to simplify the operation and to avoid too much lookup in that part of the network. We're having gateways, and in the gateways we are making a conversion from optical to electronic domain to make the repacketization of the information. We are also aiming at running different transmission rates in a different area, and finally also it might be that actually the most attractive place to have optical packet switching might be in the metropolitan area network because of the lower variations in traffic flows in the wide area network might not request this kind of flexibility. So we have looked at topologies for metropolitan area networks and for the wide area networks, and today I'll primarily present things about the metropolitan area network. The administration of resources that we're trying to target is based on the philosophy of MPLS. We called it hierarchical MPLS when we started. Today it's more or less like in line with the generalized MPLS concept. But the idea is that we have using different layers with different degrees of granularity. We might receive packets from a classical electrical MPLS network that we will repacketize or aggregate into optical package in an optical MPLS network, and then later on in the layers we'll have the administration of wavelengths, wavelength bands, or fibers, and all this interconnected. And of course that's also the idea of the generalized MPLS, but when we started we used the hierarchical MPLS, so we stick to that still in our presentations. So to start with, the metropolitan area network is built by interconnecting a number of physical rings. And with the physical ring, we mean a physical optical fiber. And we can handle a number of these optical fibers interconnected with what we call a hub, which is an all-optical switch. And inside these physical rings, we can have a number of wavelengths, or what we call logical rings. And basically, in the operation, we do not distinguish between a physical and a logical ring. Of course, it has an impact on the implementation of the ring node. But basically, we can implement the ring node so that we can access perhaps several physical rings if they pass the same ring node. But of course, with a physical ring, we can have ring nodes that are not using the same physical location. So the whole idea is that we can use the ring as a way to communicate between the ring nodes. But if we want to access the wide area network, or if we want to reach ring nodes that are not attached to the same physical ring, or it's not looking at the same number of wavelength, then we can use the hub to making the interconnection between these rings. So the idea is that we have a ring that is set up as a slotted, divided into time slots. And then we have control information that controls where the location of the different time slots is designated for, and we have also control information saying how the prioritization of the certain time slot is, whether a ring node is allowed to remove the current data if, for instance, has a higher priority, and put in its own information. So the main intelligence is in the hub, and the hub is also used to allocate capacity between the different nodes on the ring. And the next slide shows the hub functionality and what it's actually doing about the time slots. So I just take all the different parts here. So the idea of the hub is that you have a number of rings, and again, it can be physical rings or it can be logical rings, but at least if it's a physical ring, then it's been divided into wavelengths because we're only handling it as individual wavelengths when we're entering the hub. This hub just shows a hub with 4 inputs. For the demonstrator, we have implemented 16, but it simplifies the functionality to show this way. But the idea is that the hub is making a permutation of the time slot coming into the hub node. And by changing this permutation, and by dynamically changing this permutation, we can create a number of capacity connectivities between the different ring nodes and between the different rings. So this permutation is calculated, and based on the required capacity between the ring and the ring nodes, we'll make a sequence of permutations. So if, for instance, we have a permutation configuration saying that we should make this kind of permutation, then the hub will be configured in this way, and then in the next time slot we will have another permutation. And because we can do this permutation, or the reconfiguration of the switch is done in within a nanosecond or so, we can operate fairly short time slots. And in the demonstrator, we worked on time slots in the size of a microsecond. So basically, this hop works in a similar way to an old telephone exchange. And maybe we should say that the current status of packet switching is at that level at the moment. But maybe that's the right way to do it, because what it does is actually it takes the time slots and then it permutates the time slots. And a good advantage here is that in addition to the time domain, we also have the wavelength domain as a way to solve contention. But basically, we'll not have any kind of contention, because the hop will in advance calculate which ring node is allowed to send to other ring nodes. So we'll never have contention in this hop. All the buffering will be done in the ring nodes, compared to the wide area network, where we need to do some kind of buffering in the network nodes. So the permutations are based on measurements. So there will be a measurement both in the ring nodes and the hop about the required capacity between the different nodes. So the packet format that we're using both in the metropolitan area network and in the wide area network are based on fixed size packages. And there are a good reason for doing that. And the main reason is that we need some kind of synchronization. In networks where you can work with variable size packets, it's mainly in level 3 networks. When you go to the link layer, we need some kind of synchronization mechanism, and it's much easier to do if we're using fixed size packets. We've decided to do that in the demonstrator we've built, but we're also evaluating the cost and the benefit of supporting variable size packages. One of the problems is that you need a longer preamble to find the synchronization of the package, and it means that then we have to work on longer packages to justify this longer preamble functionalities. There's also some problems in loss of capacity in non-synchronized packets. So if we want to support variable service units, variable size PDUs, then we can use a slotted configuration where we allocate a stream of slots, concurrent slots in the stream, and in that way we can have the capacity available. We are looking into different scenarios for implementation of the ring node. A ring node based on available technology, you can do that now. It's not available because the market is not ready for that at the moment. Is less flexible. One of the things is that you can only drop packages. You cannot delete the package. So the time slot will not be available until it will reach the hop again. In another configuration, we have much more flexibility. We can access several wavelengths. We can erase a packet, and we can insert packet in the same title that we just received information in. In the demonstrator, we have implemented legacy interfaces here, and that's what we use for demonstrating the real-time traffic. Another administrative thing that is important in optical networks, if we step away from the technology, is how to administrate the network. And as I mentioned, in the David project, we've decided to work on GMPLS, hierarchical MPLS, MP lambda-S, whatever, as the core way of administrating the resources. But basically, there are two different ways of doing it. And unfortunately, the community do not agree on whether you should have a protocol-centric solution like the MPLS solution from ITF, or whether you should have an architectural-centric solution as proposed by ITU-T in the ASUN. And unfortunately, that has an impact on the future development of the use of optical technology in the next generation optical networks. Because a lot of the technology is there, but before we have agreement on the administration issues, it's hard to get people to work on the optimization of the components. Because I mentioned earlier that the cost reduction is probably the main reason for going into these kind of networks, because the components are still very expensive, the optical components are still very expensive, but there's a lot of potential in minimizing the cost of these devices. The switch I showed before, the hop that is making this time slot interconnection, is based on semiconductor optical amplifiers, which you can highly integrate in small devices. But still, it's very expensive to do because the market is very limited for it at the moment. So finally, I'll just make some comments about when the next generation network will become a reality and what is needed before it can become a reality. And when you talk about the next generation, it's at least something where the data path is all optical. So there needs to be a significant effort in lowering the cost and also to enable some kind of monitoring functions in the optical components. Especially the monitoring of performance is something that is missing in optical components at the moment. But also the components is mainly developed, the components we have today is mainly developed for transmission. And in transmission, the companies can charge almost what they like because there's no competitor to the optical fiber in long-haul transmission with high capacity. So that is one thing that is definitely needed. Another thing before we go on is that we definitely need a better understanding of the traffic and the performance in the core and the metro of the network. Do we need the flexibility provided by optical packet switching? And maybe we need it in the metro network where we are closer to the aggregation points, closer to the applications, but maybe we do not need it in the core part of the network. And again, it depends on whether we can rely on that aggregated traffic has a smooth profile or whether we'll retain some self-similar behavior, some long-term dependency behavior in the network. And then what I believe is also things that is keeping this area from moving faster is that we need to gain consensus on how to administrate these networks. People are fighting, and it's not very fruitful for the network. And finally, I also believe that we need to make optical networks digital. It might be something that people are not thinking of or maybe not aware of, that basically optical networks are assumed analog. And it's a very nice feature because then it has full transparency in terms of bit rates, in terms of protocols, in terms of everything. But if we want to do something clever, if we want to do label swapping, all optical label swapping, address recognition, we need to go into the digital domain. And actually, 3-hour regeneration is available in all optical domain. And if we want to do wavelength conversions, it's something inherent in the 3-hour regeneration element. So I believe also that we need to decide on going digital for the optical networks, and maybe then, of course, lose some of the transparencies that have been a high-profile argument for optical networks. So when will we see these networks become true? Well, all this dynamic administration of pseudo-optical networks with the dynamic setup of virtual containers, dynamic setup of STM1 connections on a millisecond or second scale that provides a larger flexibility, you'll probably see that in a very short time. It's basically available. If we can agree on standards, then you'll probably see all optical network functions in the data plane in 5 to 10 years. I believe that is, unfortunately, the time scale before you see that. There were some attempts on wavelength networks with MEMS devices, these mechanical devices. I believe that today there's only one company left on the market who still is commercializing the MEMS technology. It has been too unstable for these networks. And to come up with the last solution where all optical operation in all layers, where we replace all the electronics by optics, I believe are not realistic, at least not with known technology today, and I believe we should not try to aim for that. There's a long history of optical computers that we should not repeat in the networking environment. So with that, I'll just conclude and tell you that they can get more information on this website about the IST David project. There's another project also looking into the next generation photonic networks that you can find information about here. You can find a number of reports at that website. And then as I mentioned earlier, there will be a public demonstration of the demonstrator we have implemented in relation to a conference called Photonics and Switching that will be held in Paris from the 28th to the 3rd of October. And in relation to that, there will be arranged a visit to the Alcatel site for showing the David demonstrator. Thank you.
Thanks very much, Lars. I think you showed quite clearly that we shouldn't devaluate the term optical. I think we need in the future much more money for the term optical for making our networks real optical. So remember that in your policy decisions you make, that don't undervalue or don't underestimate what the term optical means. Are there questions? And perhaps not only for Lars, but perhaps other things came up for other people also. We have some time for a few questions. So
it's just before lunch. Yeah.
In your view, that the entire network, in your model of making the entire network digital by adding 3R capabilities, what do you see that doing to essentially the cost profile of building that network? Since currently adding 3R tends to add about a factor of 2, at least in large installations.
Well, what I see, the cost of doing 3R regeneration as just a normal thing in all network nodes, and doing it all optically. I don't believe that add very much to the costs, because I know that 3R regeneration is very expensive today, if you can even buy them commercially. But if you look at on the device needed to do the 3R regeneration, it's very simple. I mean, it's 2 interferometrics devices and some current control. You can do that for nothing. I mean, if you can go into mass production and make it a common device in all network nodes, you can do it for less than $1. Shouldn't be more expensive than that. I know the price now is very high.
okay, more questions? Mike?
I want to know, are you making any assumptions about the type of traffic, the traffic profile, in 3 to 4 to 5 years' time, or are you using sort of conventional breakouts of traffic, particularly in the access, the MAN, and the core network?
Well, within the project, we've done a lot of traffic studies to see, also to evaluate the penalty of having fixed-size packages when we have to map variable-size packages into fixed-size units. And we're also looking into what is the traffic profile. We're mainly looking at aggregated traffic, and we are using Pareto-distributed profiles as a common profile for the traffic we are evaluating. And also that's why we that's why we have these gateways between the metropolitan area network and the wide area network, because also as Teresa presented is that we have the ability by traffic aggregation and also making larger packages and also having some timeout functionalities to actually remove some of the self-similar behavior. So we have these kind of aspects. Traffic engineering is a very large activity within the project. Okay. Also because we need to understand the traffic to justify whether it's needed to have this kind of flexibility. So it's a very important thing.
More questions? No? Okay, I would like to thank everybody again. I think we saw a good overview of all the projects being run on optical, on real optical or pseudo-optical. And Didi gave a good overview over that. I think we saw a possible solution for a real packet switching equipment by RISA, and I think that Lars gave a good overview of all the ins and outs of real optical. Again, I would like to thank you. I think it's a step towards real optical switching. remember, I think the dinner, you have to be in time. I say it just again, I don't know the time, but be in time.